Jumping on straight into today's agenda, first I would be briefly talking about task-based workflows in Fluent meshing. So basically what I would do is in one slide, I would go over watertight meshing and fault-tolerant meshing workflows. Okay. Next, I would go over briefly, again in just one slide, talk about the Mosaic technology. And then the main focus of this webinar would be on a live demonstration where we would take in the mock-up of an X43 case and mesh it in the watertight meshing. Now we have a bunch of topics which we would like to cover in 15 minutes. So I would like to be mindful of everybody's time and complete this webinar within that time frame. All right, so let's get started. Now, in the past 3 years, the folks at Answers have put in a lot of effort to make Fluent meshing an easy-to-use tool. And a result of those are what you see here. Those are the two task-based workflows we have come up with. These have been released, I think, about 2 or 3 years ago. And then there's a lot of development which is going on into both of these. So we currently have, say, two categories of workflows. On the left, that's the watertight meshing workflow, which we call it as WTM. And on the right is the fault-tolerant meshing workflow, also known as FTM. Now, the good part for both of these workflows is they do not have a steeper learning curve, unlike traditional meshing tools. So that's the good part, right? And also, more importantly, they're very powerful and they can be used on everyday complex or simple geometries easily. Okay. Next, what I do want to mention is both these tools are highly customizable and they can be automated as well. Okay. Well, as you see in the image here, basically what you would do is you would answer a series of questions as you go from top to bottom, and then generate a mesh out of it. It's that simple. Okay. Now, the prerequisite for watertight meshing is it requires a clean watertight geometry. What I mean is you would need a geometry which has, say, for example, clean CAD and connected surfaces with no holes or intersecting parts. Okay. On the other hand, you got the FTM, which is a much more robust tool for dirty CAD. Okay. So what I mean of dirty CAD is it can handle intersecting surfaces, holes, and so on, because it is based on the wrapping technology. Okay. For today's session, I would be focusing only on the watertight meshing workflow. Okay. So briefly, let's define what is Mosaic technology. So this patent pending technology was developed by folks at ANSYS. And what it does is basically it conformally connects polygonal prisms at the walls with hexahedral elements at the core of the domain. What I mean is, if you take this geometry here, the blue part is nothing but the isotropic polygonal prisms. These prism layers, and you got the core part, which is highlighted by the hexahedral elements. And if you see in between, there are some polygonal prisms here. So the connection between these two happens conformally using the mosaic polyhedral cells. And what we have observed using this technology is that having hex core elements in the core of the domain allows for significant reduction in solver time. So we have seen about 30 to 50% reduction in some of the cases. And also the Mosaic technology gives a better quality volume mesh. Okay. I've heard that somebody mentioned there is no audio for them. I hope it's resolved and you can hear me properly. Now, before I dive into live demo of the watertight meshing tool, I just want to define the problem in one slide. So basically what I'm showing you here is a mock-up of the NASA X53 geometry. It's about 3.6 meters in length. And as you can see here, the vehicle is symmetrical in shape, so we can only consider half of it. Okay. Next, looking at the domain, It is shaped like a half paraboloid, and the domain length and all is, pretty significant of a regular hypersonic flow uh, domain. And the boundary conditions are pretty standard. I've defined the vehicle as a wall, no slip. I got the symmetry plane on this side. I got the pressure far field boundary on the other side, and there is a pressure outlet in the back. Okay, and here I call a BOI. So basically, if you've not used space claim or fluent meshing before, a BOI is nothing but a body of influence, and it can be considered like a local refinement region. Okay, so with that, I want to jump straight into a demo. So let me fire up Space Claim and load the file. Okay, let me stop presenting and shift my windows. Okay, so here is the Space Claim. Now, if you have not used Space Claim before, this is our CAD tool. Okay, what I'm showing here is the entire domain, the BOI, which I've just explained, and the vehicle is actually part of that. Okay, now what I've done additionally, apart from creating this domain, was I went into groups and then defined name selections. Name selections are nothing but labels which you define on each surface. And when you import this into Fluent Meshing tool, the tool and also next the Fluent Solver part, it will automatically detect them based on the name selections and set the appropriate boundary conditions for it. Okay, so name selections, this is the inlet, which is nothing but the pressure far field. You got the symmetry plane here, you got the outlet in the back, the vehicle is defined as a wall, and this is the BOI, which I've mentioned earlier. Okay. Now there are two ways to go from Space Claim into Fluent Meshing. The easiest one, which we would recommend, is click on the Workbench tab, go into Fluent 2020 R1, and then click on Watertight Geometry Workflow. Now, if you don't want to do this, that's okay too. So what you could do is you can just save this as a SCDoc format and then launch Fluent in a standalone mode. And you could use the meshing tool there and go from there. Okay. Two other things which I want to mention here is export PMDB. So you use this format whenever you want to read in Space Claim file into Linux, because Space Claim is not supported in Linux, and the workaround is to export it as a PMDB file. Okay. And if you have a mesh already, you could use the mesh to solver and you can jump from Space Claim to Fluent Solver directly. Okay. For this demo, we'll focus on watertight geometry workflow. So I would click on this. And as you can see, the Fluent launcher window opens up. Now here you can just select if you want to use double precision, you want to display mesh after reading, okay, and the meshing processes. Now, as I said earlier, Fluent Meshing supports parallel processing power. So you can select the number of parallel process here. But for this case, I'm just going to go with one because it's a demo. So I'm going to click Start. And sorry, I think Fluent opened up in my other screen. Let me pull that screen here. Now, basically what's happening here is Fluent is actually taking the CAD file and converting it into a faceted format. So that is what you would see happening here in the console window. Okay. So the geometry is loaded in successfully. Okay. As I said here, these are the task-based workflows. So you would basically go from top to bottom to generate a volume mesh. Okay. Couple things I want to show here is this clipping plane. So what you could do is you can insert clipping plane to check out your geometry and see if there are anything, if everything got imported correctly, or there is something just missing. Okay. In our case, everything got imported correctly. Now you could also use clipping plane in Y direction. Okay, if you don't like that view, you can just click on flip and use the slider bar. Okay, this is pretty helpful. and I'll show you why. Okay. Next, quickly, since the first step is done, if you see a green check mark here, what it means is the step is done successfully. If you see an exclamation mark here, it means that step is incomplete. Okay. Now, the first thing I'm going to do is I'm going to add local sizing. So I would say yes. And remember, I told you that we have a BOI here. So I'm going to select the BOI and say body of influence. And I'm going to set a boundary, a target mesh size of 50. Okay. And since I have draw size boxes on, so you can go in here and then see. So these size boxes represent the mesh size which you have given here. That's, it's a nice way of visualizing and then knowing what's the mesh size going to be. Okay. And I've hidden the face edges. So if you switch on the face edges, you can see all the facets in the domain. For now, I'm just going to switch it off. Okay. And we've defined the BOI. So I'm just going to say add local sizing. That's going to set up the BOI. Again, you see a green tick mark here. Next, I want to add a curvature. So for this, I'm going to select my local min size as 0.1. And I'm going to make a coarser mesh. So I'm going to set my maximum size as 15 mm. Okay. Curvature normal angle. So basically what it does is whenever you have curvatures, you could reduce this angle to make it much more refined or keep it as the default. In my case, I want to reduce it to 10. So I'm going to capture all the curvatures of the leading edge and behind in the vertical and horizontal stabilizers accurately. Okay. I'm going to select the wall. Again, as I said, I have my draw size boxes on, so you can zoom in and see, what the mesh size is going to be. Okay, so I'm good with these sizes. I'm going to say add local sizing, and lastly, I want to set the proximity size function as well. Now, if you don't know what each one does, the easiest part is you can click on these small tooltips and then read through the descriptions here. Okay, so for the proximity, I'm going to keep the size function same as to what I've put for the curvature. Okay, so 0.1, max is 15. Cells per gap, I'm going to increase it to 3, so I'm going to have much more refinement. So again, if you don't know what cells per gap is, you can just click on this tooltip. You can hover the mouse over here and then see what the description is. Okay, I'm going to scope to edges. In this way, I'm going to keep my mesh count low. I'm going to select the wall again and say add local sizing. So now we are done with the locals. We have added local sizing and we are done with that. So I'm going to jump into create surface mesh. Okay. Now you see the draw size box option is on. So you can see all these sizes here. Now I'm going to keep the minimum size as to what I've done in the local sizing here. The max size, again, as I said at the start of this, I'm going to make a coarse mesh. So I'm going to put it as 150. I'm good with these default options. And if I click create surface mesh, it's going to take about 2 minutes to create this surface mesh. In the interest of time, I'm not going to do it. And I have a surface mesh file already done. So I'm just going to shift windows and then carry on from there. Okay. So I'm going to open the surface mesh file, which you see here. So as I said, this got meshed in about 2 minutes. And I'm using a laptop. It's not a powerful workstation. So if you're using a powerful workstation and all, it might even go much faster for you. Okay. And if you want to look at how the surface mesh is, you can click insert clipping plane and then just zoom in, move this meshing tool and then see what the surface mesh is on the vehicle. Okay. If you want to know the sizes, what you could do is you could do a node selection filter and then right click at 2 different points and then click here for distance. That's going to display the distance. As if you remember, we put in a max size of 15. So it's well under that. Okay. And then I'm going to just clear the selection. Now I'm going to go to the next step and say describe geometry. Now in my case, it'll ask you 3 different questions here. Do you have solids? Do you have fluid regions? Or do you have both? Okay, in my case, it's just fluid regions with no words. I'm going to go with that. And I'm going to set the default conditions here. I'm going to say describe geometry. And if you remember, I mentioned that, once you have the name selection set in Space Claim, the boundary conditions are automatically set up for you. So I'm gonna just change this to pressure far field. I'm good with the pressure outlet, symmetry, and wall. So I'm gonna say update boundaries. Okay. It's gonna ask you how many do you want to change the region type to solid, dead, or fluid. In our case, it's gonna be fluid, which is good. And then you can jump to the last two steps. Okay, basically what you do here is you define the boundary layers on the walls. Okay, now we have four different options. One is aspect ratio, one is last ratio, a uniform and smooth transition. Basically you would use uniform or last ratio option whenever you want to have a good control of y plus all over the vehicle. Now, aspect ratio and smooth transition, you cannot get a good Y plus control, but that's okay as well, because you could load it into Fluent Solver and you can do the mesh adaptation there. Okay. So for this demo, to keep it simple, just going to use smooth transition, and I'm going to put in about 10 inflation layers. You can, if you have a complex geometry, you can select how many fluid regions you want. You can only set prism layers on separate fluid regions. Okay, I'm going to say add boundary layers. And if you can see in a minute, the green tick mark should show up here. And we go on to the last step of selecting a volume mesh. Now, as I said, we are looking at a mosaic technology. So that is nothing but a polyhex core kind of volume fill-in. Okay, we have other types as well. That you could generate a complete tetrahedral, a hex core, or a polyhedra as well. So for this, we'll go with polyhex core. I'm good with these default conditions. Okay, now remember that I've only opened this in one processor. That's why you don't see an option where it says mesh in parallel. Now, if you open it in multiple cores, you have that option of the parallel meshing, which shows up here. Okay, and if I click create volume mesh, it's going to generate a volume mesh. Again, in the interest of time, I've already generated it for you, and I'm going to show it for you here. So this volume mesh, which you see here, was generated in about 5 minutes. Okay, and you're seeing a total cell count of about 4.3 million cells. The quality was good. If you want to look at the volume mesh in detail, the best way is to insert a clipping plane, and I want to look at in this direction here, and then you can say draw cell layer. In that way, it's going to draw all the internal cell layer here. Now you can zoom in and then see how you got the isotropic polyprisms here. You got all the hex core elements in the core. And you see this is the mosaic technology where you have a conformal connection between the polygonal prism layer and the hex core using the polyhedral cells. So this volume fill type, we call this a polyhex core mesh. Okay. So if you want to look at some of the planes, you can just click on Z, or if you want to look at it in the Z plane and then just change the slider bar and click on draw cell layer, and it should show up. Now, if you're looking, since this is a demo case, I'm using just one BOI. If you're looking for your daily job, what you could do is you can have one or two more BOIs, where then you can actually control the transition of the mesh from the wall to all over towards the end of the domain. Okay, so that's all I got to show from the demo side. Let's jump on to a couple more slides from the presentation. I know I've ran over time. My apologies for that, but I just got two more slides to finish up. What I'm going to show here is the parallel scalability metrics. Now, for the same case, I've generated a much more refined mesh, which is about 25 million cells. It has about 10 inflation layers. If you can look at the graph here, as you go from 1 core to 64 cores, the volume mesh time actually went down from 60 to 4 minutes. So there's a significant reduction in volume mesh time once you start using the parallel mesh scalability. Okay, and if you look at the plot here, what it basically shows is how many million cells are generated per minute. If I start with 1 core, and if you go all the way till 64 cores, what I've noticed was for my case, it was generating about 6 million cells per minute. Okay. Now, this is for 2020 R1, which is the current release. In about a week or two, we're going to have the next release, which is 2020 R2. And there we would be supporting parallel scalability up to 256 cores. So it's going to be even more faster. And if you're dealing with much more complicated problems, you could use the parallel capability there. Okay. Now, I'm going to highlight what I've done or just show you the simulation workflow if you want to go from geometry to post-process. Okay, so basically, for these kind of hypersonic problems, what you would do is you can either create the geometry in SpaceClaim, or if you have a geometry in a third-party tool, you can import it into SpaceClaim. You can set up the name selections for boundaries. So that's step one. Step two, you would just transfer the SpaceClaim file into meshing tool. So this meshing tool is actually Fluent meshing tool. Now Fluent meshing has been there from quite some time. In the same meshing tool, we have these workflows, which I've just showed you. That's the watertight workflow. So you would transfer the clean CAD into watertight workflow, mesh there, and you can save the mesh for any future mesh edits there, or you could even automate the mesh process. It's fairly easy there. And then you would just switch to solver. So basically you would load it into Fluent solver, select the DBNS solver because we're dealing with hypersonic flows, and run the solution there. Now you can just write a journal and you can script all the steps here, which I've shown here, or you can use the GUI and do the same process. Now, once the solution is done, you can go into Fluent. You can continue staying in Fluent and post-process the entire thing there. Or we have these also some additional post-processing tools like ANSYS Insight or CFD Post. So you could export Fluent solver part into that as well. Okay. Now, last slide, what I want to show here, because I feel this is very useful for all you folks in the aerospace community. Basically, what I'm showing here is some additional capabilities which we have, which are focusing on dynamic mesh adaptation for capturing shocks. So basically, we have the capability to identify the shock layers in the solution and dynamically adapt the mesh to make it finer, specifically in those regions, so that the shock layer can be resolved accurately. Now, as an example case, you're looking at the Aerospace, the classic hypersonic case at Mach 6. Now, if you look at this mesh here, which is, I call this the refinement level 0, this is a very coarse mesh of about 20,000 elements, and you can see that the shock layer is basically not captured and the shock part is diffused everywhere. Now, once you use the dynamic mesh adaptation for shocks and you keep refining it at about refinement level 10, you can see how well the shock layer is captured. Now, the beauty of this algorithm is you can just set the required parameters and let Fluent do the mesh refinement and coarsening in appropriate regions automatically, right? So basically, you don't need to sit there and then change any settings. You would just set your pre-requirements in a single window and click run, and Fluent will automatically refine from this stage to this stage, and you would have a nicer mesh which would capture the shock layers. Okay, on the right, I'm showing you a couple videos which basically highlights dynamic mesh adaptation on the mesh, and in the bottom video it shows how the shock layer is moving when you look at the Schlieren contours. As you refine the mesh, the shock layer is being captured pretty well. Okay. Now, summary. What we have looked at in this mini webinar is we have looked briefly at the Fluent workflows. One is a watertight meshing workflow, and second is the fault-tolerant meshing workflow. And next, I've shown you the Mosaic polyhex code technology. So basically what it does is it uses the parallel capability and it accelerates the meshing time. And we have also noticed that using the polyhex code technology versus only polyhedral cells, there is a significant reduction. It's about 30 to 50% in the solver time. Okay. And next we went through a quick demo for watertight meshing workflow on a high-speed markup of the X43 case. And lastly, what I want to say is the task-based meshing workflows, which I've shown, are very easy to use, and they're very easy to learn if you're a new person into meshing. Okay. If you're an already experienced user, that's even great because you could use these workflows and you can actually customize them a lot so that it will suit your problem appropriately. And it's not only for simple problems, these workflows can handle complex geometries as well efficiently. Okay. And lastly, you can automate the entire process from CAD to mesh using scripts as well. Okay. That's all from my side. I thank you all for taking the time today and attending this webinar. I know I've received a bunch of questions. We would try to answer them after this. Okay. And I hope you all have a good holiday weekend and stay safe. Okay. Thank you.